Tech Nuggets, IPv4 Subnetting. This topic is kind of long and complex. We're going to talk about how to take larger blocks of v4 addresses and turn them into smaller networks. And we might need that for security reasons or address reasons or routing reasons. There are a number of reasons that we would want to take larger blocks of v4 addresses and cut them down into smaller. Maybe our ISP gives us a large block and we need to turn around and cut them down. And we'll be covering that. This nugget is a little longer than some of the other tech nuggets that we've done because the topic is kind of complex. And I'll be covering a number of different analogies, ways to think about subnetting that are similar to other tasks that you might do in your everyday life. And then at the end, I'll be going over a method for showing subnetting in kind of a visual way. Doesn't really use a lot of math, doesn't use a lot of binary. We talk a little about it, but the method I've got is more of a gamist theory where we can look at it visually and sort of divide and talk about it. I'll also have some tools for doing quick subnetting. If you're a student, that'll be maybe for an exam. And if you're a working person, that would be the kind of thing you might pull out and use as a reference when you need to do that kind of stuff, but it doesn't happen very often. So let's start this discussion with what is subnetting similar to? Things that maybe you've done every day. You don't really think about it. It's that same mental division that you would do in a number of different parts of your life. And the most common one is making change. Imagine you're standing at the cash register, somebody hands you $1, and you need to make change. There are a lot of different ways to make change. The other way that we might think about it is dividing up parts of a number line. We've looked at number lines in elementary school and primary school, different ways to divide up the line, by 2s, by 10s, by 5s. Subnetting is not dissimilar from that idea. So let's turn it into a game. How many different ways can you make change for $1? You're standing at the till, like I said. Somebody hands you a $1 bill and says, "Can I have change?" Now some of this is, well, geez, we could sit and do math and figure out all the different ways to make change for $1, right? I can, I can give him 4 quarters, I can give him some dimes, I can give him 100 pennies. There's a bunch of different ways to do it. Or I could, if you're more computerized, you could write a program that would go through and do that kind of thing. Turns out there are 293 ways to make change for $1. You think of the ways that you can easily make change, like I said, maybe 4 quarters and things like that, or you can do the math. And in fact, I've listed a link here that will show you someone that's gone through and done the math for how many different ways to get that 293 ways to make change for $1. And you might ask, what's the point? Well, the point here is that when making change for $1, most people have several go-to combinations they start with. 4 quarters is usually the go-to when you say, "Can I have change for $1?" And there's a number of reasons for that, right? We think about, oh, you need change for the parking meter, and quarters are usually what you'd put in a parking meter, or maybe a pop machine, or something like that. So we have some kind of go-to mental models that we start with when we get to that. And when solving a problem like subnetting or change for $1, we tend to go to the solution that's the easiest to remember, and then we derive more answers from there as we need to. In our example, if our cash drawer is out of everything except 2 dimes, 65 pennies, a quarter, gosh, I guess I can sit down and figure out how to make change for $1. I'll have to sit down and do some math and sort of think about it for a little bit, since our go-to answer didn't work. And that's not uncommon. When we do subnetting, we'll start with kind of a common go-to answer, and then we'll derive down to the specific need as we get there. All right, so the next example here is a number line. And we can see this number line here grows from 0 to 10, so it's a 10-point number line, and we're going to divide it into 4 equal parts. Most people can look at this and go through it and divide it in half, and then divide the halves and halves and get to the answer without a big problem. This is the second number line, and we're going to look at this number line, and it goes from 700 to 1700, And if you're clever, you'll realize it's pretty much the same number line that we just had up, and we'll divide it in half and divide the halves into halves, and that gives us 4 equal parts. And you might ask, what's the point? Because really the only difference between the two number lines were the numbers on the line. Both were 10-point number lines. The intervals of the numbers were the same. But most people get really caught up in the math of the question. They want to immediately pull out long division and try to do division and figure that out. They want a calculator to try to work with it. Most of the time, the number line is just used to sort of visualize the division process. You put your finger about a quarter of the way along the number line, or about halfway and then halfway again. And the math you should do should be pretty close to that number if you were to sit down and actually do the long division or the calculator. And if it doesn't, it probably doesn't pass what I would call the smell test. Something smells funny. It probably does if it smells funny. Subnetting can be done with this similar kind of visualization as the number line. Do you really need this? Yes, you really need this. Subnetting is a blocking topic, and that means if you don't understand subnetting, you won't be able to use subnetting to do more advanced networking topics. It's a mental construct that everybody that's going to work with networking and networking equipment, designing, architecture, any of those kinds of stuff are going to need. And this slide is really to encourage the student to make sure they understand it before they go on, because shortly after this, in the networking world, the student will be very, very lost. So if you're a student, work with your faculty and instructors or any other resource, online, video tutorials, until you understand. It is critical that that go on and that the understanding happen. And that's part of the reason I'm making this video, is to help students to understand. So if you go through the whole video tutorial and you don't get it, go back and watch it again. Go find a different tutorial. Go find an in-person instructor to explain it to you until you understand. It's that important. I'm going to work on a non-mathy way to show that. We find that a lot of our students are not math people, and that they would prefer to learn in a different way. Maybe obvious from previous slides, maybe not. I'm a gamer. I'm a computer gamer, a paper pencil gamer. I enjoy games. I use them to help teach topics. And while games in education isn't a new idea, gaming as a subnetting tool is a fairly new concept. So we'll lay out the basics. Games have rules. Why? Because otherwise they aren't games. You can't win or even play without rules. And some games you don't really win or lose, but all games have rules of some kind. We're going to treat subnetting as a game. And when it comes to games, rules are rules, and sometimes it doesn't matter why those rules exist, they just do. When we talk about Monopoly, it doesn't matter why the rules in Monopoly are the way they are. No one questions the rules. You might have an argument with them, but they are the rules of the game Monopoly. If you want to play Monopoly, you read the rules and play them. We're going to treat subnetting the same way. We're going to lay out a set of rules, and they're going to be that way. If you want to understand why the rules are that way, that's when we have to start getting into the math and some of the binary discussions. But if we just want to believe that the rules are the way they are, then we can treat it very similarly to a game. The rules of the game. And the rules in this case are ordered from unbreakable to change as needed. And this game is a little different than Monopoly, where most of the rules apply all the time. In IPv4 subnetting, we're going to have a kind of a scale of continuum of rules here that are going to go from rules that you just straight up can't break to rules that we're going to change as we need to because the boss needs us to change or our design needs that to change. And those rules are going to be the binary law, meaning, and we're going to go over each one of these rules. There'll be a slide and a little discussion that goes with each one. We'll have a binary law, which is pretty much unbreakable. And I realize I said I wasn't going to have any math, but I will explain what that means with very little math or no math. We have an N-2 rule, which is mostly unbreakable, although there are a few times it happens. We're going to have where's my gateway, what's my static IP address, where's my DHCP. These are conventions, and they tend to be what makes the most sense. And then we get along to things like business needs, like, wait a minute, my boss wants me to divide it up. Why? This way? Or best practice in my industry is, or I read the white paper on this product and it says I need to do this. Those are business needs, and they're important, but they're a little more malleable than some of our other needs. And then we have what we would consider at the end, which is the most elegant design. And a lot of people would say, well, wait a minute, shouldn't that come before a business need? No, business needs come first, because that's how we stay employed, is by making sure that we get the business need covered. Our most elegant design incorporates the business need, because our most elegant design is what can make all the equipment work the best is not always what our business need is. We'll go over each one of these next. The binary rule. This is a pretty much unbreakable rule. At the bottom of this whole subnetting mess is some mathy stuff based on the binary system, which is the system the computer uses to count. It's a core concept that divides it. For us, this will turn into being very specific about how we divide our networks. And that means all networks must be divided in half, equal halves. For our analogy with the dollar, that's going to mean we must turn a dollar bill into two 50-cent pieces. Every time we divide, we're going to divide it into two equal halves. The N-2 rule. And this is mostly unbreakable, and I'll cover sort of the corner cases where that's not true. When we divide our network, there are two addresses that are lost. I put that in quotes here. They're lost. They can't be assigned to a PC or to a host, is the other term for that. It can't be assigned to an actual working piece of equipment. That's the first IP address in the range and the last IP address in the range. The first IP address is known as the network number, and we'll use that in routing and in talking about and referring to the entire subnet. The last IP address in the range is known as the broadcast address. And there are a few times that gets used, but we're not really going to cover what that is or means. It's suffice to understand that in the N-2 rule, we lose that. Network numbers, as I said, are used in routers to direct traffic. Think of it kind of like a zip code for everybody that's in that subnet. I've not really been shown where network addresses are useful, but they're part of the rules. Stupid or not, they're still part of the rules. The N-2 rule. Because of this rule, there are some really tricky word problems. And for my students, that means they could come up on the exams and have come up on exams. When people ask you, how big is the subnet? And you say, well, does that mean with or without the two that I subtracted? An inclusive range, please note the word inclusive, will mean the total size. That means including the N-2. How many usable addresses are in the network is different than what's the total size. How many usable addresses means how many can I actually assign to hosts? And that means you need to take out the two for the N-2 rule, because as I said, the first and the last are not assignable to machines. So usable addresses in a network is different than total size of a network. The usable addresses in the network would be considered an exclusive range, which means we exclude the two on either end. Conventions. The next sets of rules get a little more, there's a little more wiggle, there's a little more gray, and how do I set these up? We're going to go over a set of conventions here that we use in our labs and our classes, but if you're out in the real world, there may be some different conventions that people use. They pick them up from consultants, they pick them up from when they were in school, they're picking them up from a business need. So your mileage may vary in this case. We're going to talk about a gateway IP or a router IP, and that's the computer that's able to pass traffic from your side of the network where your host might live to the rest of the network on the outside of the world. That gateway may also have multiple functions. It may be your router and your NAT and your firewall, but from a strictly IPv4 sense, in our case, we're going to talk about it as a gateway IP or a router IP on your local LAN. What IP does this have? This IP will count as part of one of the usable addresses in your usable address space, but it has to live somewhere. We might also have a range of numbers that we set aside for static addresses. You might have older equipment that doesn't do automatic address allocation very well, and so you need to set aside those. Things like servers often have static addresses. Why? Because we want clients to be able to find them, and if their address is wandering all over the place, can't find that. So we give those statics, whereas other people on the network may, standard client, my phone, my workstation, I'm not really that worried about what my address is, but it's where I'm going to on my network that needs to not move. The last discussion here is DHCP. There'll be another lab that talks, and video, that talk totally about what DHCP is, Dynamic Host Configuration Protocol. And it's a method for clients, like your workstation or your phone, to get an IP address. But it's a pool. That means there's sort of a big range, and it gets a random one out of the pool. And like I said, in most cases, we're not worried about what my address is. I'm worried about where I want to go to. So we may need to lay out those inside our usable address space, so that way we can say, okay, I've got enough addresses for all my clients, I've got enough for some statics, I've got one for my router. We'll need to lay that out in a documentation kind of style, and in a design architectural documentation style, we'll do that. All right, and then comes the business needs, and this is where it can get really, really, we'll say customized, I think is the nice way to say that. All the other rules have kind of been leading up to this. Odds are you work at a business and the business needs to get work done. And if we can't get the work done, we don't get paid, and that means we don't have the money to pay you. So business needs are critical needs, and we're working up to that in terms of making sure our design and architecture works that way. Business needs can be all over the map, and I'll use a couple that are kind of absurd, but I assure you have happened in real life. The example that I use here is that the boss is not a super technical person, and they like, quote, their IP. They can remember it, they've had it for a long time, and they've mandated as part of their business needs that their machine is going to keep that IP address, and whatever design and architecture you come up with better work around that. It sounds totally absurd. I assure you it's not. A more realistic or maybe less funny example would be, I have a shop floor filled with equipment. That equipment is old. It needs to all have special IP addresses. It's very difficult to change them. We need to work around those pieces of equipment, and everybody else's machine can change, but these pieces of equipment are not changing. And that may throw some real wrenches in how your design and architecture lays out. But it is a need, and we're going to work around it. The elegant design. Good design starts with an efficient IP subnet architecture plan. We want the least wasted space, and that's when we talk about N-2 rule. Remember, we're losing 2 out of every subnet, and if they only give you 256 addresses, every time I chop it up, I'm going to lose 2, and that can be very inefficient. We still want to get our business needs covered. Good network admins plan for the future. I have just enough to make it work. Wait a minute, is there going to be growth here? Do I need to worry about that? Maybe I should leave some space in my subnets for growth or change or things like that. In the next video, I'm going to go over an example along with the visual tool for showing block subnetting. So stay tuned on the next video. We'll go through a detailed example.